So for video 3, we're going to look at exponential modeling. We're going to do a few models that are fairly common in the context of exponential functions. The first big idea is setting up a growth and decay model. So the growth and decay model looks like this. There's going to be some quantity that either grows or decays over time. So for example, if you put money into savings, your money will grow over time. If you take a potato out of the oven, the temperature of that potato will decay over time. So there's a lot of things that either grow or decay according to a specific growth rate or decay rate. And this is one type of model for growth and decay. So the idea is Q, the quantity that's either going to grow in size or decay in size, is going to be equal to Q naught. And Q naught represents the initial quantity that you start with. Q naught is the initial quantity. So for example, we could look at putting money into a bank. Maybe we deposit $100 into a bank and our Q naught would be the $100 that we initially deposited. And then you're going to have something that grows. And it's going to have a growth or decay rate. So R is the growth or decay rate. And this is either as a fraction / decimal, because a decimal is a fraction if it's terminating. So the rate of growth or decay. So for example, if we're working with a bank that's going to pay us 4% interest on our $100, then we would take 4% and the rate would be the conversion of that 4% into its decimal form or its fractional form, 4 over 100, which simplifies to 1/25. So I could use either a fraction form or the decimal form of the rate. And then T is the number of times that the number of time units that you either grow or decay that item. It could be measured in days. T could be time in days, where you have something growing or decaying a specific way every certain number of days. Or T could be time in months. T could be time in weeks, in years. So you usually set some baseline for what T is going to be. There's going to be a time growth increment. And T is going to be measured in those time increments, frequently days, months, or years. Those are probably going to be the more common time increments, sometimes months. So T is just your time, growth time, or decay time. So we could look at how much money are we going to have 3 years after we deposit $100 into an account at 4% interest. And the idea behind this 1 plus R is that we can take the amount that we have now, which is 100%. So Q naught, the initial amount, always starts at 100%. And then you're going to say plus some rate. So plus some rate. So for example, 4%. And this adds up to 104%. So at the end of 1 year, you should have 104% of what you started with. And as a decimal, this is just going to be 1.04, because to convert from percent to decimal form, we just move the decimal point 2 places. So that's all this is doing, is adding 100%, the amount that you have to begin with, plus your growth rate. So the 1 in that equation is just representing 100%. And so the idea is really simple. The idea is this. The idea is you start with an initial amount. Say, so we got our Q naught is 100. And if I let Q sub 1 be the amount of money I have a year later, to find that out, I would need to take 100 and I would multiply it by the 1.04. Right? I'm going to add 1 to the 0.04. And if I multiply that out, I get $104 1 year later. To figure out how much money you had in year 2, what you would do is take the amount of money you got in year 1, the $104, and now this money grows. So you would you would take 104 and you would multiply it by 1.04 to figure out how much money you had in year 2. But the other way that we can think of 104 is as 100 times 1.04. So you take 100 times 1.04. This is the amount of money you have 1 year after your investment. And to figure out how much it grows in the next year, you multiply it by 1.04 again. 100% preserves everything that you had the previous year, and the 4% adds on the growth. And this is really just 100 times 1.04 squared. And we want to recognize that this is really just 100 times 1.04 to the first power. And in fact, at time equals 0, it's really 100 times 1.04 to the 0 power, because anything to the 0 except 0 itself is going to be equal to 1. So to figure out how much money you had in year 3, you would just take 100 times, hey, the 1.04 squared, that represents the amount of money you had in year 2. This is Q2. And you multiply it again by 1.04. But that's going to give you 1.04 squared times 1.04 is just 100 times 1.04 cubed. So to come up with this formula, it's the same kind of idea. You say, hey, I start with Q naught, and the amount that I'm going to have 1 year later, Q1, is just going to be Q naught times my growth rate, and really it's going to be to the first power. And Q naught here would be 1 plus 4 to the 0 power. In year 2, how much money would you have? Or how much of the thing that was growing or decaying would you have? Well, you would have what you had from the previous year. This is your Q1. And you multiply it one more time by the growth rate. But that just gives you that thing squared. And notice this is time. This is t. This is time t. This is time t. So to figure out what you have in year 3, you would take the Q naught times 1 plus 4 squared, that represented what you had the previous year, year 2, and you would multiply it by the growth rate again, which would just give you Q naught times 1 plus 4 cubed, and there's your time equals 3. And you'd continue this pattern. So in year n, you would have Q naught, and it would be 1 plus r, and notice that the number that goes here is going to be 1 less than the current year because it's the previous year. So you get n minus 1 times 1 plus r to the first. And to simplify exponents, you do n minus 1 plus 1 because the bases are the same. So you get n minus 1 plus 1 is just n. And that kind of establishes where this formula comes from. You just take, to find out the amount that you have in time equal t, you take the original amount, Q naught, and you multiply it by your growth rate, 1 plus r, and you raise it to the tth power. So here's an example. So we have a dentist estimates that her dental equipment loses 1/6 of its value each year. So our time increments are years. T is in years. And our rate, R, is 1/6, except we're losing value, so it's actually negative 1/6. And it says, write the model for the depreciation of an X-ray machine that costs $216,000 new. So this right here is our Q naught. This is the initial price of the X-ray machine, and the value of that machine will depreciate or decrease over time as the machine gets older. So the model needs to follow that Q, the thing that's growing or decaying, equals Q naught. How much did we start with? 1 plus R. R is the rate of growth or decay to the t. So I don't want to use Q. I'm valuing an X-ray machine. So I'm going to use V for value. The value of my machine as a function of time is going to be equal to Q naught, which is the initial value of the machine. And I do need to remember that I'm constructing a model that's in thousands of dollars, times 1 plus my rate, but my rate is negative 1/6 to time, which is just going to equal 216,000. 1 plus negative 1/6 is 6/6 plus negative 1/6 is 5/6 to the time. And there's my value model for the depreciation of the machine. And it's an exponential function. The base b is 5/6. My variable t is in the exponent position. And I have a stretch of a factor of 216 of being applied to the toolbox function 5/6t. So part B says, determine the value of an X-ray machine after 5 years if it costs $216,000 brand new. So the value as a function of time, but I'm being asked to put 5 years in for time, and years match my model. So I plug in 5 equals 216 times 5/6 t, but t is going to be 5. And then we can use a calculator to approximate this. So two ways to do this. I'm going to go ahead and keep that. So if I'm using a graphing calculator, I would just turn on my graphing calculator, and I would do 216 parentheses 5 divided by 6, raised to, using the caret button, the 5th power, and hit enter. And this is 86.805. So there's a couple ways I could think about reporting my answer here. 2 ways that would be pretty reasonable. So one way to think about this would be to say, hey, my model's in thousands of dollars. So I could say, hey, I'm going to round it out to 3 decimal places, 86.806. But because my model is in thousands of dollars, I can move that decimal place 3 places and say, hey, the approximate value of my machine is going to be $86,806. So that would be one approach that might be reasonable. And the other approach might be just to say, hey, I'm going to keep my model in thousands, which means I just need these first 2 digits. I got a 0.8, so I'm going to round it to $87,000. So I think either of those would be decent answers. $86,806 or $87,000 would both be pretty reasonable ways to report out an answer. I got to get my pointer back here. If you don't have a graphing calculator, and I know some of you, because of the situation that we're in, don't have one, you could use a tool like GeoGebra to do this. So if we had GeoGebra, what I would do is I would probably just go ahead and type the model into GeoGebra, and I would do it in function notation. So I have v of t, but GeoGebra won't take a t, so I'm going to have to replace t with x as my input variable, and I would go equals 216 times, put in parentheses 5 divided by 6, use your caret button and raise it to the x power. And initially you're not going to see anything because this function's stretched by a factor of 216. So let's think about this for a minute. If I'm trying to graph this, and I've got v of x equaling 216 to the 5/6 times 5/6 to the x. Where is it going to cross the vertical axis? This is the time axis. Where is it going to cross this axis? Well, that happens when time equals 0. So when you plug in 0 to the model, what do you get? You get 5/6 to the 0 is 1. You get 216 times 1 is just 216. So the graph is crossing the axis way up at 216. So we've got to resize this window to be able to see the graph of the function. So in GeoGebra, a simple way to resize the window is to go to the graphics view, select that, then hover over the axis until you get the vertical arrows, and then left click and hold and just drag down. And it will quickly resize your window. You can drag down or up to resize. And you can see up here about 216 is where the graph is crossing the time axis. And then we wanted to know how much the value was at 5 years. So there's two ways I can go about this. One's going to be satisfying and one isn't going to be very satisfying. But I did use function notation right here, v of x. So I could just directly plug in v of 5. The only issue is that the default in GeoGebra is to give me the exact answer, which is frequently nice, but probably in a case like this where we're talking money, it's probably not the best way to report out the answer. So the other way to do it is to realize, here's my input of 5. My output's going to be on the line right here. And what we can do is actually put the ordered pair right on the line. So if I go down to the input bar, down here, I'm going to make an ordered pair. I'm going to say, hey, I want to know when the input is 0, comma, not 0, when the input is 5, comma, what is v of 5? So put the 5 into the function notation. Put the 5 down here into function notation, and then just hit enter and plot the point on the graph. And when you plot the point on the graph, what you're going to see is that you can come over here and get your 80. That time equals 5. The output is 86.81 or $87,000 if we round it. And if I want to see more decimal places, I can go into options and rounding and say, hey, I was in thousands of dollars, so I want to see out to 3 decimal places. And there's my 86.806 that we got from before. So we can play the same game that we did just a moment ago. We can say, hey, I'm either going to round it to the nearest 10, because that would really be $87,000. Or I'm going to take it out to all 3 decimal places because I know that the model is in thousands of dollars. I know that's going to add 3 extra places on, so I could estimate my value at $86,806. I think either of those would be pretty acceptable ways of handling this particular problem. Let me get my grabber back, minimize these for a moment. Oops, I got to bring this open. I got to wipe that window out and bring that back. Bring the PowerPoint slide back up. Okay, so we determined the value after 5 years. Now part C says determine when the machine is worth less than $125,000. So we're wanting to know when the value of the machine is less than $125,000. So the way that you do this is you determine or ascertain when is the value exactly at $125,000. You find the t value for which that's true, and then you say any time past that point in time, because the item's depreciating, it will be worth less than $125,000. So we really, if we're setting this up in an algebraic sense, we would be replacing the value in the function right here with the 125, and we would be asking the question, when is it equal to 216 times 5/6 to the t? And this is something we don't know how to solve yet. You need logarithms to do this, and we don't have them, so we're going to use a graphical approach to finding the solution. Now, it'd be similar to what we did in video topic 2, or video 2 for topic 15. So I'm going to go back to my graph in GeoGebra. I'm going to close out my window here. And I've already got the function graphed. I already have the right-hand side of the function graphed. Here he is. Now I'm going to graph the line y equals 125. I'm just going to go y equals $125,000. And where 125 intersects with my model v of t, where the intersection is, that's where the value is going to be exactly equal to 125,000. And then for any time to the right of that point in time, the value will be under 125,000. In fact, the value is decaying to 0 over time as the machine gets old. So I'll just take my intersect tool and grab that intersection. And it looks like from right here that $125,000 will happen in year 3. So after 3 years, the value of the machine will be less than 125. So I'll go back here, I report out that final answer, and then I say something like, for t greater than 3, my value of my machine will be less than 125,000. So finding that graphically. So the next example, we're going to do Newton's law of cooling, and a number shows up in Newton's law of cooling called Eulers number, named after the person who probably discovered it. I think it's after the person who discovered it, but sometimes those are apocryphal stories, so I better be careful what I'm saying here. So Eulers number E, it's about 2.7-ish. It shows up in modeling applications where you have continuous growth or continuous decay. That's going to be a number, if you go on to calculus, this number is going to play a big role, especially when you're doing differential equations. It shows up in population models, logistic models, shows up all over in mathematics, and is important enough so that it gets its own calculator key on your calculator. So Euler's number, something that we'll explore more deeply if you take calculus, but for now we're going to say, hey, if x is greater than 0, Euler's number is the number that you get if you take this expression right here, 1 plus 1 over x to the x, and you let x go to infinity. We've been talking about end behavior of functions. The end behavior of this function, 1 plus 1 over x to the x, approaches the number e as x goes to infinity. So we've given the number that this approaches a name. And that's going to be all that we do with it for right now. If you grab your graphing calculator, I'm going to go ahead and keep that. If you grab your graphing calculator, the button right here, the button on the graphing calculator that says ln, which means natural logarithm, and we'll go over that later this week. Right above it, there's a button that says e to the x. So if we turn on the calculator and we hit second ln, it will give us the e to the x, and if I put a 1 in, that'll really be e to the first power, and the calculator will approximate Euler's number for me. So Euler's number is about 2.718-ish. That's how you'd get them on your graphing calculator. If we're in GeoGebra, I can dump the number e into the input bar, and it's going to approximate at 2.72. I can go into options, rounding, and grab more decimal places, and I'll get the approximation for it showing up right here. So just a quick overview of what E is, just because we need to use it. We're not going to say too much about it for right now. So Newton's law of cooling, this is our last example for this particular video. Newton's law of cooling is it comes from differential equations. If you are a math major, you will derive this formula from scratch later on. So Newton's law of cooling says that the temperature of the object as a function of time is going to follow this model. This T sub r that you see right here, this is the temperature of the room. This is room temperature, or I prefer ambient temperature. So this is just the constant temperature of a surrounding medium. So for example, if you put a potato into the oven, the potato, you've preheat your oven to 425. Once the oven's preheated, now the ambient temperature, T sub R, of the oven that you're going to put the potato into is 425 degrees. So ambient temperature is the temperature of the media that's surrounding something that you've put into it. So the oven might be 425. You put the potato in, the potato is going to begin to heat up, and it's going to try to approach the temperature of the oven over time. The potato will heat and try to get to the temperature of the oven, and that's how we cook things. So T sub R, ambient temperature, temperature of surrounding medium that is either going to heat or cool something. T naught is the temperature of the item to begin with, temp to begin with. So if the temperature of the potato was 60 degrees when we started, that would be T naught or T sub 0. And there's the ambient temperature again, showing up twice in this equation. Ambient temperature. K is a constant that depends on the physical properties of the thing that is heating or cooling. We don't know how to find K yet. We will know how to find K in about a week. But what's going to happen for now, when you have these types of problems, they're going to tell you what K is because we don't know yet how to find K. And then T is just the time increments that you're working in. Minutes, hours, days, weeks, years, whatever the measure of time is that you're using. The idea is this T naught minus TR. The idea is that as the temperature of the object No, I'm not gonna. I'm gonna step back and not say anything there. So we're just going to use the model. Is what we're going to do. And later on, we'll develop models from scratch. If you move on into like a course in differential equations, or even at the end of Calc 1, we usually derive this formula from scratch. So if a can of soft drink is taken from a 35-degree cooler and placed in a room where the temperature is 75 degrees, how long will it take the drink to warm to 65 degrees Fahrenheit? Assume K is about negative 0.031. So we need to establish what the room temperature is, or probably shouldn't say, I don't like the T sub R. I probably should say the ambient temperature, T sub R. What is the ambient temperature? And what is the temperature, initial temperature of the object that's heating or cooling? And sometimes students will get those two things kind of mixed up. The idea is the ambient temperature has to be the temperature of the medium that is warming or cooling the object. And in this case, we put the soft drink into a room. The room, which is at 75 degrees, will begin to warm the pop up until the pop gets very close to 75 degrees Fahrenheit. So the ambient temperature is 75 degrees Fahrenheit. The temperature initial, T naught, of the soft drink is going to be 35 degrees Fahrenheit. It's 35 degrees Fahrenheit when it's pulled out of the cooler and placed in a 75 degree Fahrenheit room. And of course we were given K. So it says, how long will it take the drink to warm up to 65 degrees? So the first step is to set the model up. First we need the model before we can do anything with the model. So the temperature as a function of time of our pop is going to be modeled by the ambient temperature T sub R, which is the 75 degrees that the room is, plus T naught, which is the initial temperature of the object, minus, and that's minus T sub R, and T sub R is the 75 degrees that the room is at to begin with. And then it's going to be e to the K, so we replace K with negative 0.031 times time. And so there's the model. The model's been set up. And we want to know how long it's going to take the drink to warm up to 65 degrees. So to figure that out, we're going to need to replace T, temperature, with 65 and set it equal to 75 plus 35 minus 75, so we probably should do that subtraction. That subtraction is going to be what? Negative 40 times e to the negative 0.031 t, and the plus and minus, we can actually clean that up just a little bit. That's going to just be a minus 40 e to the negative 0.031 times time. So here's our model, and just like before, we don't currently know how to solve this. We don't know how to get a variable out of an exponent position. Not yet. We will soon, but not today. So we're going to go back to the calculator world, which is the only way we have to do this for right now. I'm gonna exit, bring GeoGebra up, and let's get ourselves a new window, and don't save the last one. So I'm going to type the model in first. So temperature as a function of time, but I can't use t, so I'll use x, equals, our model is 75, and we had plus the 35 minus 75, which is a minus, I can just type in minus 40, and then it's e, and you just write e, it's Euler's number, the computer will recognize it, e to the parentheses negative 0.031 times x, and then hit enter. And I did not do a good job of typing that in, so we're going to try it one more time. Temperature as a function of x equals, it was 75 minus 40 e to the parentheses negative 0.031 x, and then I can type enter, and there it is. And again, like in the previous example, we're not seeing the function because I need to resize my window. The pop is starting at 35 degrees, and because the pop starts at 35 degrees, I expect my temperature graph to start at 35, and my temperature is going to increase to 75 degrees, so I probably want to get the graph up where I can see the 75 degree mark on it. So that's where the temperature is heading towards. And then we wanted to know a specific temperature. I'm going to type in y equals 65, enter. I did a minus instead of an equal, so it's telling me an invalid function, equals enter. And again, we want to find the intersection. Here's my temperature model. Here's the temperature line, 65 degrees. When the model gets to that line, my pop will be at the 65 degree mark. So I'm going to grab my intersect tool and mark that intersection, and then I can come over, this is the point A, I can come over to the algebra window, look at A, and this says, hey, 44.72, what's my model being measured in? It's being measured in minutes. We got a minute model. So 44.7 minutes after we put the pop in the room, it will be at a temperature of 65. We'll call this about 45 minutes. So I'm grabbing the input variable right here because this is my time axis. So this is t and this is temperature. So about 45 minutes, and then we just report out the final answer. We say after about 45 minutes, the temp will be about 65 degrees. And then I'm gonna make a comment here because the slide actually has a construction issue on it. So you have for time, I knew that time was minutes because I knew time in minutes was used to come up with this value for k. So it should have been indicated to us that time was being measured in minutes, and it wasn't. So usually in the homework problems, you're going to have something that more explicitly delineates the time to you. the value of k is dependent on the time increments that you use to find k, and in this case minutes was used, and it's not explicitly stated on the slide, so that's a mistake on my part for not catching that.